How do we find a function f such that when we take the gradient of this function f, we are going to obtain back our main function, which is our vector field. This small f is simply potential function. So when we take the gradient of the potential function, we are going to obtain the vector field f. So this is it. Let's partial f partial s to be equals to y squared, and partial f partial y to be equals this guy. We have 2sy plus exponential 3z, and the same thing with this. The third component, we have partial f partial z to be equals 3y exponential exponential 3z. This is 3y exponential 3z. So we can consider any component, but let's consider this first. So consider this. We have partial f partial s equals y squared. So let's integrate both sides. When we integrate both sides, we have f equals integral y squared dx. So we have f to be equals, when integrate with respect to x, we have sy squared plus some constant of integration, because we are dealing with function capital F, which is a function of s, y, and z. So, and we integrate with respect to x. So our constant of integration will be a function of y and z. So the next thing to do is to, let's call this equation 1. So differentiate equation 1, which is partial f, with respect to y. So we have 2sy plus h subscript y comma z. So if we differentiate this with respect to y, we're going to have h subscript to y of y comma z. So we can compare this equation that we obtain here, partial partial y. You can see it's the same thing as this, partial partial y, but what is it is equated here is different. So when we equate these two guys, 2sy is gonna eliminate each other, so we're left with hy of y comma z, and z which is equals to exponential 3z. So now, since the value of h subscript y is this, we can plug it in here. So we have partial f partial y equals 2sy plus exponential 3z. So let's call it okay. Let's integrate both sides. So integrating both sides, we have f to be equals to integral 2sy plus exponential 3z dy. So when we integrate with respect to y, we have f to be equals 2sy squared over 2, because this is considered as a constant. If we integrate with respect to y, we have 2sy squared over 2 plus integrate this guy with respect to y. This will be a constant, so we have y exponential 3z plus some constant of integration, so which is h of z. H of z is our constant of integration with respect to y. When we integrate with respect to y, we have our constant of integration to be h of y, h of z rather. So we can write this as, this is 2, this is 2. We can write this as sy squared plus y exponential 3z plus h of z. So now let's call it equation 2. Equation 2. So now differentiate the equation 2, which is this. Differentiate with respect to z. So we have partial f partial z equals, when we differentiate this guy with respect to z, we are going to obtain 0. There is a z here, so when we differentiate with respect to z here, we have 3y exponential 3z plus, and we differentiate h of z with respect to z, we are going to obtain h prime of z. So we obtain a beautiful expression here. So we can compare this guy, partial f partial z, with this that we obtain, partial f partial z, which is this. We can compare it with this. We have 3y exponential 3z here, and we also have 3y exponential 3z here. So when we equate it, we are going to obtain h prime of z equals to 0. So integrate both sides with respect to z. We have h of z equals this beautiful constant, which is k. You can write small c, p, just a constant. So we have h of z equals to this. Now there is h of z here, and there is h of z we obtain here. We can now plug in the value of h of z here. So we have f to be equals to s y squared plus y exponential 3z plus k. This is simply the potential function, which is small f, that we are looking for. Let me show you from the question. This is what we are looking for, the small f. And the question says, if f capital F equals this guy, find the function f such that when we take the gradient of this potential function, small f, we are going to obtain the capital F. So let's do it. This is simply the final answer, but let me show you. When we take the gradient of f, let's say we take it with respect to x first. So check, let me just write check. This is simply the final answer. But when we take this guy with respect to x, this our function, we are going to have y squared. This will be 0, this will be 0, just constant. So we differentiate, we have y squared. You can see we obtain y squared from here, the first component, the height component. So let's say we take a derivative with respect to y also. So we have, this will be 2sy plus exponential 3z. So let's compare. You can see we have 2sy plus exponential 3z. So let's also differentiate with respect to z. And with respect to z, we have this guy will be 0, and we are going to have 3y exponential 3z. This will be 0. So let's compare. So we have partial f partial z to be this. So this is indeed our function f, such that when we take the gradient of this potential function, we have a capital F, which is our vector p. So we are done with the proof. Thanks for watching.